Okay, so hello everyone. Thank you all for being here. My name is Gabriel Marin, and today I'll be your host. I'm thrilled to introduce you to Valerie Domcke from CERN and EPFL. To tell you some background about Valerie, she did her undergraduate studies at Technical University of Munich. Then she obtained her PhD at DESI in Germany. She also held a postdoc position at CSI in Trieste, and now she is a researcher at CERN and at the Swiss Federal Institute of Technology Lausanne, or EPFL. Her fields of interest are beyond the standard model of phenomenology, cosmology, and astroparticle physics, and gravity. Today, she's presenting about proving the scale of grand unification with gravitational waves. So thank you, Valerie, for accepting our invitation, and feel free to start your talk when you're ready.
Yeah, thanks, Gabriel, and thanks a lot for the invitation. I mean, I think this is one of the great advantages of these Zoom talks, right? Because flying over to you guys would have been slightly more complicated than what we're doing now. So yeah, I'll be talking about how we can use gravitational waves to probe the very early universe. And the idea is a bit what is on this title slide, and that is that so this is a picture of the evolution of our universe from, on the left, very early times when the universe was hot and dense, until here on the right, the universe after it expanded the way we see it today. And using gravitational waves, we can really, in principle, probe this entire spectrum. And this is different photons, right, which is our usual probe to learn about the universe. So with photons, we can only probe back to the time of CMB decoupling, because at earlier times, the universe was simply not transparent to photon. So that is, in principle, the great promise of gravitational waves, that we can really get up to these very, very early times, very, very high energies, in principle, up to the scale of grand unification or beyond. But okay, so this is the great promise, but then as we'll see in the talk, there's also great challenges. And yeah, I invite you to ask questions also anytime during the talk. It's always a bit difficult to make Zoom talks interactive, but yeah, I'm very happy if you ask questions. Okay, so the outline will be as follows. I'm going to split this talk essentially to two parts. So in the first part, I'm going to talk about a source for gravitational waves that I'm currently very excited about, which is gravitational waves from metastable cosmic strings, and I'll explain in a second what that is about. And then in the second part, I'll talk about new ideas of detecting very, very high frequency gravitational waves in the kind of the megahertz to gigahertz range, because this is the typical frequency that you expect for sources from the very early universe. Okay, so let's start with the cosmic strings. So the standard picture is that cosmic strings are topological defects, which are formed in symmetry breaking processes in the early universe. So the simplest picture is what I've depicted here. So you have a U1 symmetry, so a kind of a scalar potential like this in field space, and then you have a symmetry breaking process, and you get this Mexican hat potential. And now in different spatial regions, the field will kind of roll down into different parts of this Mexican hat rim. And so you get a field configuration in real space, which can have topologically non-trivial features. So in particular, you can imagine you can have one part in space where kind of the VEF of the symmetry breaking field is say pointing outwards in all directions, as like in a ring-like structure. And now there's no infinitesimal transformation that can kind of make these topologically non-trivial object go away. And this topologically non-trivial object will precisely be a cosmic string. So a one-dimensional thing, which is somehow winding through field space, where everywhere in space, you're kind of in a true vacuum, but at the core of the string, you kind of restore to the false vacuum. So you still have this vacuum energy of the symmetry breaking potential. And more generally, this happens, I mean, more generally, when I'm talking about field space and real space, so what's happening is I'm mapping the vacuum manifold of my symmetry breaking process onto real space, and I'm asking kind of if this can be done in a trivial way or not. So mathematically speaking, we say that we form cosmic strings if and only if we have a symmetry breaking process G, some group G going to some smaller group H, and we get cosmic strings if and only if the first homotopy group of the quotient group of G over H is non-trivial. Okay, and once, and this is like this kind of, U1 symmetry breaking is the simplest case where precisely this happens, and where we can kind of imagine what's going on just by kind of drawing arrows on a board. Now, once these cosmic strings form, they evolve. So you can, the strings can then kind of intersect each other, or they can intersect with themselves, chopping off little loops. And the loops can now start oscillating and can start radiating gravitational waves, shrinking in the process. So in total, what happens is that due to this splitting off of loops and the shrinking of the loops, you get into this so-called scaling regime, where the fraction of energy which is in cosmic strings is always a fixed fraction of the total energy density of the universe. And this is kind of true as you go through radiation domination and then later matter domination. So this is an old story. This is known since well, I mean, this picture is from the 90s. Now, the kind of the interesting observation now, which I would like to make, is like, okay, what if we actually like look at realistic symmetry breaking processes when we link the standard model to the scale of grand unification, right? So consider, for example, an SO10 gauge group, which we break into standard model across U1. It could be U1 B minus L here. This is very motivated in this context, but it could also just be, we don't have to identify it. And then this breaks down in the end to the standard model gauge group. So if we now look at just the second symmetry breaking process, then essentially what we're breaking is just U1. This is exactly the example that I had on the first slide. And this should give you cosmic strings, right, according to what I just discussed. Now, you can, however, also look at the entire symmetry breaking process at once, right? You start from SO10 and you go all the way down to the standard model. Now you have to work a bit harder to compute the first homotopy class of this quotient group. But if you do it, what you find is that this is in fact trivial, which means that you actually don't form cosmic strings. But now this somehow cannot be, right? Because I mean, this is a kind of a mathematical question, and it has to have one answer. And you know, you cannot. I mean, either you form cosmic strings or you don't. So this is a bit confusing, but this confusion was actually resolved already in this old paper by Vilenkin, who was saying, well, you do form cosmic strings, but they're not topologically stable, because in this first symmetry breaking process, you first generate monopoles. These are zero-dimensional topological defects, or point-like topological defects. And then in the second process, you generate a string, as we discussed. And now you have a gas out of monopoles and strings. So the strings kind of latch onto the monopoles. So the strings now have ends, whereas before the string could not have an end. Now the string can have an end. And then it just kind of, the whole this string monopole gas just decays away very, very rapidly. But now the interesting observation now for us, if we want to, if we're kind of thinking about gravitational wave signals, is that you could have a situation where between this first symmetry breaking step and the second symmetry breaking step, you could have a phase of inflation. Because I mean, one of the reasons that inflation was invented was precisely to dilute away the unwanted monopoles from such symmetry breaking processes. So the idea is you first generate the monopoles, then you have some cosmic inflation, you dilute away the monopoles, now you form the strings. The strings do not see the monopoles anymore, right? So naively, you will think, okay, now you just form a stable cosmic string network. However, the strings, I mean, these monopoles are still valid objects in your quantum field theory, despite that you've diluted away all the physical realizations, which means that you can now generate these monopoles as string pair production along the core of the cosmic strings. And this production rate will be exponentially suppressed with the mass ratio of the mass of the monopole divided by the string tension. So essentially, there's a ratio of this symmetry breaking scale and this symmetry breaking scale. And so if the two symmetry breaking scales are very far apart, then this exponential suppression is very large and the strings are effectively stable. But if these scales are somewhat close together, and we'll see what somewhat means in a second, then these strings could kind of have cosmologically long lifetimes, but still kind of decay over the life of the universe, hence modifying the standard picture of cosmic strings that I discussed on the previous slide. And that's precisely what I call metastable cosmic strings, and this is kind of which will lead to the gravitational wave signal that I'm currently excited about. So how do you compute now a gravitational wave signal? So here we're talking about the gravitational wave signal from these metastable strings. So this is going to be a stochastic gravitational wave signal, so not kind of the transient type of signal that we know from black hole mergers and that we've observed with LIGO, but instead kind of some sort of isotropic signal really coming from the early universe and reaching us as a kind of a stochastic noise signal, something we have not yet detected. So if you want to compute the gravitational wave spectrum, so this is the energy in gravitational waves per frequency, per unit frequency per total energy density of the universe, then what you need to know is essentially the power spectrum. So the key contribution here is coming from the loops which are radiating the gravitation, loops which are oscillating and which are radiating the gravitational waves. So you need to know the gravitational wave power spectrum of a single loop. This is Pn, where n denotes the harmonic of the loop in which it is oscillating. So we'll have the sum over n. And then we need to know the number of loops which are emitting gravitational waves such that the frequency at which we observe it is f today, because this is the spectrum observed today at frequency f. But to compute this quantity, we need to take into account also the redshift of the universe, right? Because depending on when this gravitational wave was sourced, the sourcing frequency has to be different, such that the observed frequency today is always this frequency f. So this is the complicated part, this green box. And you get, in order to compute this, what you need is the distribution function of the number of loops with a given length and a given time at any given redshift, because the length of the loop is via the harmonic directly related to the frequency at which this oscillating loop is emitting. And of course, we need to know the cosmological history, because we need to take into account the redshift of the frequency. So the key uncertainties in this process is to know this loop number density, which you can to some degree obtain analytically, and to some degree kind of then there's three coefficients, which then to some degree are determined by big numerical simulations. And that is still kind of a major source of uncertainty to kind of really pin down this loop number distribution function. And the other uncertainty is kind of here this Pn, so to understand exactly what is the gravitational wave power spectrum of a single loop, because that kind of depends on how much substructure there is in the loop on these questions. So these are kind of things which there's studies on. We're kind of using the results from, do I have it maybe here? No, I don't have it here, but yes, we're using these results from this paper here, right, which is based on the largest simulation that has been done to date. But I should just say that there is some discussion in the literature and that things have not completely converged yet. So up until here, this is essentially the standard story for computing gravitational waves from cosmic strings in the so-called Nambu-Goto approximation. So where you take the string width to be small compared to all other dimensions of the problem. Now, the only thing that essentially changes once you consider metastable strings is that you take the loop number density of the stable strings, and then you need to factor in the decay of the strings due to monopole production and gravitational wave emission, right? And this gives us exponential suppression factor here. And then this theta function here takes into account that you can only have the loop production in the initial phase, kind of before actually the monopole decay rate became efficient. So this exponential function, so this part is essentially the new ingredient, which comes from the observation that the cosmic strings can actually have a finite lifetime instead of just being the age of the universe. So with that, we can plug this back in here, and we can compute the gravitational wave spectrum. And so this is what we get. So here we see the gravitational wave spectrum as a function of frequency. These dashed gray regions are future experiments. The solid gray regions are existing experiments, right? So here's LIGO. Here's a pulsar timing arrays. This orange is the hint, the nanograph hint, which I'll talk about more in a second. And then these other lines are the predictions for different values of G mu. So this is the parameterizing the string tension. And kappa is the ratio, I recall, of the monopole mass to the string tension. So essentially the ratio of the SO10 breaking scale to the U1 breaking scale. So we see that we need, and essentially what happens is that if kappa or if square root of kappa becomes larger, particularly if it becomes larger than 9 or so, right, then the lifetime of the string becomes longer than the age of the universe, and then you get these black dotted curves. This would be kind of the previous result. And now, because we have a finite lifetime, the gravitational wave spectrum gets cut off at low frequencies, because low frequency is kind of what is sourced in the late universe. And then as we make kappa smaller, so here going from 8 to 7, you see the cutoff happens at higher and higher frequencies. And this is interesting because, for example, this G mu times 10 to minus 7 roughly corresponds to the gut scale. And for stable strings, this is simply ruled out, right? So this will be this black line here, and it's like way above the existing PTA bounds, right? So the pulsar timing array bounds for stable strings limit G mu to roughly 10 to minus 11 or so. But for these metastable strings, because you have this suppression at low frequency, you can easily have this blue curve, for example, right? So you could have a suppression of at the scales of pulsar timing arrays, but you could have a huge signal at LISA, and you could be right around the corner for LIGO. So this is kind of really a chance for LIGO in essentially the next observing run to put constraints on a gut scale phase transition, which is not in contradiction with the non-observation of gravitational waves in pulsar timing arrays. So for stable cosmic strings, the prediction will be LIGO cannot see anything because these bounds are strictly stronger. But for metastable strings, there's a real possibility of LIGO to see something. So this is an idea that can really be tested in the very near future and could, in principle, tell us something really about the scale of branch unification and about kind of the details of the symmetry breaking process. So let me comment a bit more on this, or maybe this would be a good point in case anybody has any questions.
Yeah, I can ask a question.
Sure.
So, are there any other interesting topological defects that can be relevant for this discussion? Okay, apparently monopoles are not, but what about higher dimension, like textures and stuff? I cannot remember what's the discussion there.
Right. So there was a paper, a very recent paper by David Domcke and Hitoshi Murayama and collaborators in Berkeley. And they essentially looked at, because here we essentially are studying this scenario of strings spontaneously decaying via the production of monopoles. Mm-hmm. And what they looked at is domain walls spontaneously decaying via the production of strings. So everything one dimension higher. And so they really, you have to make the domain walls unstable, because stable domain walls would just overclose the universe and you will just be ruled out. And so there they have the interesting scenario that both the domain walls and the strings emit gravitational waves per se. And then the precise spectrum depends on, exactly how the domain walls formed, when are the strings formed. And then they can either get a broad spectrum like here, or they can get a very peaked spectrum at high frequencies. So that's also totally a possibility. It depends, it really depends. I think in that paper, they also, I'm actually not even sure the paper's out. So they gave a talk on it. I'm not even sure if the paper's out, but otherwise I'm sure it'll be out shortly. But they had a nice graph of the different symmetry breaking processes. And depending on, how you break, what sort of topological defects do you get, and in what order do you get them, and then correspondingly, how would you compute the gravitational wave signal?
Yeah, cool.
Okay, so let me then comment on this orange thingy, right? So this orange thingy is the tentative signal from nanograph. So nanograph is a pulsar timing array. So the idea is that you observe pulsars which are sending a very, very regular light signal to Earth, right, just due to the rotation of the pulsar. And then you measure the arrival times of these light signals. And then the idea is that if a gravitational wave passes between you and the pulsar, it would distort the arrival times in a specific way. And this you could then kind of use to detect gravitational waves. Now, of course, if you just use one pulsar, there's kind of many things that could distort the signal, right? It could be something internally to the pulsar, or it could be, I don't know, some asteroid or something, right, passing between you and the pulsar. There's many things that could do this. So what you do is you actually use a network of pulsars, and you kind of observe the arrival times of all these pulsars. And then if you get delays in the arrival times, you need to check if the spatial correlation of these delays is consistent with the hypothesis of a gravitational wave causing them. And so what they observe is, this was last summer, what they observe is that they find strong evidence of a stochastic process with a common amplitude and spectral slope across all pulsars, right? So it's something that is not like some noise in one pulsar which is not understood, but it's something that is kind of consistently occurring across all pulsars. And then they look at the angular correlation, and this orange line would be the monopole signal. So this would be kind of what you would expect if, I don't know, you just have some trivial noise source in your instrument. This blue line is the so-called heading down correlation. So this is what you would expect if it's actually a gravitational wave signal. And these gray violins is what they observe. So you can see the error bars are still large, and it's simply a bit inconclusive, right? So the monopole signal is definitely not favored, but it also seems that this Helling's down curve is also not a perfect match. So yeah, the status is we have to wait, right? So the status is there is they see evidence of, you know, some excess noise, but if this excess noise is really gravitational waves or not is currently an open question. And then a year later, so like now, recently, another pulsar timing array, the POX pulsar timing array, also put out an analysis. And they analyze their data using the same methods as nanograph. They have a similar amount of data, and they found a very similar signal. So here is now kind of, so they depict this in terms of the amplitude and slope for this kind of noise source that the additional noise source that they find. And here, so these dashed dotted lines are the nanograph lines, and these blue lines here are the POX lines, right? So more or less, I mean, yeah, I mean, they overlap, right? So more or less they agree. And then this is again the Helling's downs curve. This black line is what you would expect for gravitational wave signal. The red is the observation. So again, kind of not conclusive that it's a gravitational wave, but also you cannot rule it out, right? So again, we have to wait. And it's also not surprising that this is kind of similarly good or bad than the other, right? Because they have the same amount of data. So kind of the statistical power is expected to be very similar. So we have to wait, but while we wait, we can chase an ambulance, right? And we can ask if the signal that they observe would be compatible with metastable cosmic strings. And if yes, what it would tell us about the parameters that we need. So here I'm showing the amplitude of the gravitational wave signal at 3 nanohertz, which is the peak sensitivity of these pulsar timing arrays, versus the slope at these same frequencies, right? So essentially, this is, in spirit, this is the same plot as here, right? Amplitude versus slope, just that I kind of plotted in the dimensions, which are kind of more natural for cosmological signals. And so these orange lines is the nanograph signal, these black ellipses here is the PTA signal, or the PPTA signal, and this colored mesh is our prediction for metastable cosmic strings, where again, these colored lines vary G mu, so the string tension, and along the line, the dots vary this kappa parameter, so the ratio of the two symmetry breaking scales. And okay, you see that there is a range for different values of G mu, and for some values of kappa typically around 8, or square root of kappa around 8, where you are in reasonably good agreement, in particular with the PPTA data. So you can then ask, okay, now what if I compare that, because you remember this plot here, right? Kind of seeing a signal here has implications in this model for LISA and LIGO. So we can ask the question, can we test? So say nanograph kind of confirms the Helling-Downs curve, right? And say we get convinced this is a gravitational wave signal. Then of course it could also be, that doesn't mean per se that it has to be metastable cosmic strings, right? In particular, the more minimalistic explanation would clearly be that it's supermassive black hole mergers, right? Because if in doubt, it's always astrophysics. But we can still, we could test this hypothesis, right? And we could see, okay, in the parameter space of G mu and kappa, which is the only two parameters in my model, can I test the nanograph hint by independent observations? And in particular, in blue is the region that LIGO can cover, right? So currently the LIGO bound is, well, either this line or this line, depending a bit on how they do the analysis. And this is how far LIGO would get with design sensitivity. And the entire region I'm showing here will be covered by LISA, right? So if this is a signal from metastable cosmic strings, then there's a clear prediction that LISA should see this with a huge amplitude. So this is something that can definitely be tested. Now zooming out on this plot, right? I mean, if we say, okay, maybe we don't believe in this hint, right? Or maybe this has nothing to do with cosmic strings and it's astrophysics, then we can still ask the question, how well can we probe this parameter space with upcoming gravitational wave observations? And so this is the same thing on the axis kappa and G mu, but now zoomed out a bit. And so this orange this was before the plot is old, this is before the nanograph hint. So this is essentially the exclusion limit from pulsar timing arrays, where the hint is just here at the border of the exclusion region. And then here you see the sensitivity of LIGO, sensitivity of LISA, the exclusion region of LIGO, exclusion region from the CMB. And this hatched region is the region that we, essentially the reason why we initially even started working on this project, because this is something that goes back to my time as a PhD student, and was kind of a nice cosmological model, which, you know, did a bunch of nice stuff, like in particular producing dark matter, producing the baryon symmetry, and was actually, however, kind of had a very well-defined string tension. And so this is kind of to show that, you know, here there's really a realistic model which you can really probe with these type of observations. And yeah, so this string tension is really related directly to the symmetry breaking scale of the U1. And so if you're looking for and here, so here I'm showing the well, okay, so here here's the string tension. Here on the top axis, I'm relating this to the breaking scale of the U1, or here the mass of the monopoles. And so hence you see why this is really probing dot scale physics in this parameter range here. Okay, so that's, I think, all I wanted to say about the metastable cosmic strings as a gravitational wave source that I'm currently excited about. So again, if there's any questions on that, this would be a good time. Otherwise, I'll move to the second part of the talk.
Okay, I will ask another one. So it's again related to the first bit, where you showed the prediction for the power spectrum from the scaling network of the strings in your very first slides.
This one, or
no, the formula. You had some template.
This one.
I think even before. There, this one. Yes. So you said that, okay, there is some analytical insight, and you use also simulation to get these omega gravitational waves, right? But
right.
So is it a very complicated thing at the end of the day? I mean, are there simple templates that you can fit this thing and just look for it in the data? I mean,
yeah, absolutely. So in the end, so okay, so the thing which is complicated, right, is this loop number density,
right,
and this power spectrum here, right? And so the loop number density, you know, it's so here, so for example, here I give the formula for the loop number density in the radiation regime. And so you can get essentially the parameter dependence you can get analytically. This essentially comes from simply so first you kind of convince yourself that the scaling regime is something real, but then once you then know that you have the scaling regime, right, you can essentially get the parameter dependence here analytically, and the only thing you get from the numerical simulation is this prefactor, the 0.18. Okay, so this is kind of a free parameter if you just do it analytically, and then the numerical simulation kind of tells you which number to put here. But this is actually a very simple function, right? So it gets, and also this Pn is actually something very simple, right? It's some So again, it's some power law, right? So it gets a little bit complicated only because you have to sum over n. So hence it's kind of like you don't want to do it by hand, right? But it's nothing that is very complicated to do with like Mathematica or something. And actually, I mean, for practical purposes, I mean, unless you want this to very high precision, it's completely fine just to go to n equal 10 or something. And the high precision, okay, we do it to do things correctly, but in the end, the uncertainty that you have in this number is probably larger than the uncertainty that you get by summing tons and tons of modes here.
Right. And another related thing, why are we always talking about the scaling regime? Because this is only where we know how to compute things, or?
Right. So the scaling regime is an attractor solution. Okay, so again, very at the beginning when we form the cosmic strings, everything is like super chaotic and non-linear and complicated, right? And this you can also cover in simulations, as in particular simulations by Mark Hindmarsh and company, who do field theory simulations of the symmetry breaking process. So they can really study also this very early phase. But then after some time, you asymptote to the scaling regime. And once you're in the scaling regime, you stay in the scaling regime. So this very early time where things are very chaotic is only kind of happening in the very beginning. But at the very beginning corresponds to, say in gravitational waves, right, corresponds to extremely high frequencies where we don't have any detectors.
Okay, that's fine. Yes, I understand that. Okay, cool.
But now I'll shortly be telling you that we should be building detectors there. But this is one of the reasons why people don't care so much about this initial phase. So A, it's complicated, and B, it's unobservable for the moment.
Cool.
Okay, so that's perfect, right? This brings me to the second part, and that is very high frequency gravitational waves. So the plots that I was just showing, right? I just cut them off at some point, and I cut them off here because this is essentially kilohertz is essentially the limitations of how far we can get with existing detectors. But this signal continues, can continue typically up until megahertz, gigahertz or something. Because megahertz, gigahertz roughly corresponds to, something which is sourced at the horizon size in the very early universe, right? So say at temperatures of around grand unification or something, right? Or a bit below, with high reheating temperatures in the early universe, you have some cosmological process which is roughly horizon size. It produces gravitational waves. These gravitational waves get redshifted until today. And then the frequency of these gravitational waves, very, very generically, is megahertz to gigahertz. So from a cosmology point of view, this is a very, very interesting place to look. From an astrophysicist point of view, it's a very bad place to look because there's no astrophysical objects that could source gravitational waves in that frequency regime. Because you'd need, in order to do this kind of with an astrophysical object, you'd need something which is kind of very small, very compact, and like even more compact than a black hole, and that simply doesn't exist. This on the other hand, this means if you see a gravitational wave signal in that frequency range, it has to be new physics. And we have no known physics that can produce gravitational waves, sizable gravitational waves at these high frequencies. So in some sense, it's a background research. Then of course, well, depending on your search strategy, there's a lot of noise, which is not straight gravitational waves, right, but other stray stuff. So roughly what is the idea? So the idea is that, okay, if you're a theorist, you plot this omega parameter that I was showing you as a function of frequency, and you have all your beautiful BSM models. And the only constraint that you have beyond your creativity is that you have to respect the BBN bound, which tells you that you're only allowed to add a certain amount of extra radiation to the universe, right, without kind of destroying observations from BBN and CMB. And gravitational waves as kind of massless radiation fall into this category, right? So they have to kind of respect the delta N effective bound. But that's the only limitation that you have. This is a straight line in this plot. Underneath this straight line, you can do whatever you want. And in particular, you could come up with beautiful models of PSM physics in the early universe, which give large signals over here in the high frequency range. Now, if you're an experimentalist, you don't do this plot. You plot something else. So you have also frequency on the x-axis. However, you're not actually measuring energy, you're measuring displacement. And displacement is related to energy via, so essentially the energy parametrically is displacement squared times f squared, meaning that at high frequency, this BBN bound plotted in this plane becomes a lot more severe. So even if you are building an experiment at high frequencies, which is the exact same strain sensitivity as, say, LIGO, you're now suddenly miles away from actually detecting anything of cosmological relevance. So when going to high frequency, you essentially have two problems. So one is that this BBN bound suddenly becomes a lot more severe and a lot more difficult to beat. The other thing is that this strain sensitivity is essentially a relative displacement. So to draw this plot, right, to have the same sensitivity to relative displacement means you need an even better sensitivity in terms of absolute displacement. So doing this with an interferometer type experiment just seems completely hopeless, because LIGO already is measuring absolute displacement of the size of a proton, right? So it just seems that you cannot push this very much further. So we need new ideas. So we had the first workshop in Italy in 2019, where we gathered a bunch of experimentalists and theorists to kind of develop or talk about kind of crazy ideas, how we could ever look for gravitational waves at high frequencies, and just to kind of understand if this is at all feasible and kind of what is out there regarding proposals. And then we had a second workshop only 2 weeks ago, discussing more concrete proposals, again, bringing together experimentalists and theorists. And honestly, so both workshops, all the talks are online. And I must honestly say, I was very baffled by the progress that have been made over 2 years. Kind of here in the first workshop, we were really already completely struggling just to understand each other, right? Because people were talking about omega and other people were talking about H, and like, how on earth do we compare, right? And what are we even talking about? Now I kind of feel like it became much more clearer kind of what of the technologies kind of presented in this first workshop are actually kind of potentially promising, and how they've been developed, and like much more noise sources have been taken into account and so on. And also then there were new proposals for new technologies which had not been discussed in this first workshop. So it really seems to be a rapidly evolving field, you know, where you can actually kind of half of the experimental talks on this workshop were actually given by theorists who had kind of come up with you know, some fun idea how you could try probing these gravitational waves. And since, you know, currently nobody has an idea how to actually get down to here, so even if your idea is kind of crappy and is kind of miles away from this BBN bound, since, you know, everybody's idea is miles away from the BBN bound, you're kind of justified to put it out there, which is kind of fun. So this came out as a living review, which we just kind of got published in a living review on general relativity. And this plot is essentially, in some sense, this is a summary of the first workshop. So this plot kind of summarizes the different types of sources that we could kind of think of for the early universe in this kind of gigahertz range, megahertz to gigahertz range, and the different kind of experimental proposals that are out there. And here, this dashed line is the BBN bound. So you can see all experiments. So the solid ones are essentially existing bounds, so sometimes with some ranges, and the empty boxes are kind of proposed experiments. And you can see like and this is like, I mean, this is a log scale, right? Going from 10 to minus 10 to 10 to minus 40, right? So everybody is still quite a ways away from this magic line. But it's kind of interesting to see how very different type of experiments that could be relevant, right? So here's an example. This is ALP, so this is here. This is an axion light shining through the wall experiment, so big, relatively big experiment. But kind of they recycled their axion limits and used them as gravitational wave limits. And then here, on the other hand, these bulk acoustic wave devices, this is this pink block here. These are very, very tiny devices, which are essentially kind of resonant mass type devices. So the idea is kind of the gravitational wave shakes this device, and you have a clever way of detecting that. So I just put these two examples to show you kind of how very, very different types of experiments could be useful in this frequency range. So in the very last few minutes, I just want to introduce you to one idea that Camilo Garcia-Celi, a postdoc at DESY, and I put forward about using radio telescopes as gravitational wave detectors precisely for this frequency range. And so the idea is that you can have, just simply if you combine kind of gravity with electromagnetism, no new physics at all, right? And you can see that there's a conversion of gravitational waves into photons in the presence of an external magnetic field. So this is very similar to the maybe more familiar process of conversion of axions into photons in the presence of a B field. This is precisely what we use in the ALPS experiment. But the same vertex exists also for gravitational waves. Of course, this interaction is extremely tiny, right? You have a 1 over m Planck here. So our idea was to compensate the very tininess of this coupling by using a huge detector, and namely a detector which is the size of the universe. So we want to utilize cosmic magnetic fields in order to kind of convert some primordial gravitational waves into some stray photons, and then we want to detect the stray photons using radio telescopes. Now, this has always the disadvantage compared to a lab experiment that everything is much less under control. And in particular, there's huge uncertainties on what are actually the magnetic fields on intergalactic scales. So there's upper and lower bounds on this, but we simply don't know yet what are the B fields. And so we can, instead of putting a bound, we can put a range of bounds. So here are our results using now recycling the results from EDGES and RK2, which were two radio telescopes. And so we're showing constraints on the characteristic strain as a function of frequency. And the colors indicate the assumptions on the B field. So if the cosmic B fields are as strong as current astrophysical bounds allow, that gives us the strongest bounds here. So then we would be in this purple region. Whereas if the gravitational waves are as weak as allowed, meaning as weak as compatible with the blazar hints, then we would have this yellow line here. For comparison, these Roman letters here are various laboratory experiments. So you can see that even for moderate magnetic fields, we're actually doing quite a bit better than the laboratory experiments. But the ineffective bound, so the BBM bound, is this generically this dashed line here, right? So the really truly primordial cosmological signals are expected to live down here. So again, we're whiles away. You can somewhat wiggle your way around this, right? Because if essentially if your gravitational wave source was active after CMB decoupling, right, then you're not subject to this bound. Or if you have a very, very spiky signal, then the bound is modified. But in absence of kind of doing, yeah, so but the generic expectation will be that the signals are likely to be down here. So we don't yet have the sensitivity to get here, but this was also just kind of recycling existing data, right? So maybe kind of more dedicated searches and more advances in this radio astronomy and kind of in 21 centimeter astronomy may be able to push this a bit further. And of course, the key uncertainty is also knowing the cosmic B field, right? So kind of in order, I mean, okay, you can, in order to put a robust bound or even to claim a detection, and you would need to A, kind of push this technology, and B, have an independent measure of the cosmic B field. So yeah, that's kind of where I want to leave this, right? So I think this is kind of And it was an interesting idea, an interesting game to play. And I think it's kind of just one out of several ideas which are out there, where kind of people are really still very much experimenting on what is the most promising technology for that frequency range. And I think it's simply still a very much an open question. So with that, let me conclude. So in the first part of my talk, I focused on these metastable cosmic strings, which are a fairly generic byproduct of grand unified theories. Like it depends, exactly what type of topological defects form depend on the kind of type of symmetry, with different steps in the symmetry breaking process, and it depends, of course, on which grand unified theory you're working in. But having these metastable cosmic strings is not something very uncommon, right? It happens in quite a few models. And it's kind of interesting that you can get large signals in the entire frequency range where we have experiments. And in particular, you can get large signals even at LIGO without being in conflict with a non-detection in pulsar timing arrays. Or even you could kind of play the game further and kind of hope that maybe nanograph and the Parkes pulsar timing array have even kind of seen a first glimpse of this signal, but that's a lot more speculative. So I'm very much looking forward to kind of upcoming data, because every bit of data we get really already cuts into the parameter space of these models. And then in the second part of my talk, I was talking about the high frequency frontier, and kind of trying to encourage people to put forward crazy ideas, because we really don't know where the journey is going to take us there. And I want to finish with a quote from Meissner, Thorne, and Wheeler in a paper they put out in 1974, where they said that such detectors, and they were talking about laser interferometers, have so low sensitivity that they are of little experimental interest. And this is, of course, exactly the type of detector that LIGO is, right? And it's exactly the type of detector that got this gentleman a Nobel Prize just a couple of years back. So I take this as a sign of hope that even things that we think are crazy and hopeless today are worth exploring, because every once in a while you actually do get the jackpot. So thank you.
Thank you, Valerie, for your wonderful talk. We have some time for questions. So if anyone has one, please go ahead.
Hi, Valerie. Sorry, I missed the first part of your talk. I arrived a bit late. But I was wondering whether you will say that there is some signal that some primordial signal regarding gravitational waves that has to be there, we like it or not. And perhaps this is more related to the first part of your talk. And therefore, that signal has to be searched. And
right. So I'm just seeing if I have it on here. No. So there is. There's not even on this plot. So no. Like the what I had in the first part of my talk is really. I mean, if there's no. I mean, the first part of my talk, right, relies on having phase transitions in the early universe, right? Having some sort of grand unified theory or something, right? We are not obliged to have that, right? So this is kind of what's a completely build a consistent model of cosmology without that. So there are two signals which I think we have to have. So one is the signal from inflation. I mean, have to have, right? I mean, you can also argue that you don't like inflation, but I think that there's a really strong case for inflation. And there is a gravitational wave signal from that. And for that, however, we only have an upper bound. Right, we have an upper bound from the search of the tensor to scalar ratio at CMB scales, and that translates to an upper bound for the gravitational wave signal, and that is at about, I think, 10 to minus 16 or something in terms of omega. And then if you look at this plot, right, this plot even stops at 10 to minus 14, right? So there is a signal from inflation, which I think is essentially guaranteed. However, the amplitude is at most 10 to minus 16. And that's assuming that the tensor to scalar ratio is just around the corner in CMB observations, which of course does not have to be the case, right? So this signal can in principle be arbitrarily small. Then there's a second signal, which I think is guaranteed to be there. And that is the so-called cosmic gravitational microwave background. And the idea is simply that, gravitational waves or gravitons, right? They essentially decouple. They're so weakly coupled to the standard model that they decouple essentially immediately. But like if you have a very hot thermal plasma, then you do also produce gravitational waves just from this thermal plasma, again with 1/m Planck. And so depending on essentially the reheating temperature, so depending on the highest temperature that you reach in the universe, you get a signal. So the frequency, so the type of the signal is actually very similar to the CMB, right? So you expect it to be also roughly black body type spectrum, redshifted in the same way as the CMB, so also kind of peaked around the kind of gigahertz range, 100 gigahertz range today. And the amplitude depends on what was the highest temperature in the universe, right? Because there's a suppression factor, highest temperature in the universe divided by m Planck to some power. And if that temperature was kind of Planck scale, then that would be kind of a similar magnitude in the CMB. Of course, the temperature cannot be Planck scale because we have bounds from inflation about what can the highest reheating temperature be. And so realistically, you have to be at least a couple of orders of magnitude below the CMB signal. And then, of course, again, we don't know what is the reheating temperature, right? So if you have some low-scale inflation model where you only reheat to just above BBN, then this is a tiny signal, right? So we don't have any guaranteed cosmological signal which has a sufficiently big amplitude that we're actually guaranteed to see it, unfortunately.
This is, let's say that we measure something in, on some hopefully near future. What about the statistics? Does people talk about doing statistics with the signals? Like I don't know, like what's the kind of statistics that people will work with? Is like similar to with the CMB or?
Yeah, good question. Okay, so we're looking. Okay, so the kind of the leading order expectation is that we're looking for an isotropic Gaussian unpolarized stochastic background, right? That's kind of the naive leading order expectation. Mm-hmm. Now, so one thing, and it's okay. Now you can go beyond this in several ways, right? So one thing that I think is very important is to actually do anisotropies. Now, and one reason this is very important is, for example, that you're going to have astrophysical gravitational wave signals which are sourced by the galaxy, and so that's going to be very not isotropic. And then you're going to have kind of other astrophysical signals and possibly cosmological signals which are sourced extragalactically, right? So they're going to be more homogeneous or more isotropic. So you really want to kind of distinguish the two. Now, unfortunately, the resolution of gravitational wave detectors is very crappy, the spatial resolution. Like it's essentially like like LIGO. If you look at the response function of LIGO, it's kind of a ginormous dipole. And so if you can get up to L equal 10 or something with LIGO or LISA, that would already be fantastic. To be compared to, hundreds and thousands of multipoles that we have with the CMB. So we do want to do that type of analysis with the stochastic gravitational wave background, but it's going to be much more limited, right? So we do want to also do kind of sky maps and anisotropies, but the spatial resolution is really, really bad. And then another thing you can do is you can kind of try and get data on polarization, right? I mean, this is in some sense, again, this is similar to the CMB, right? So you can here distinguish between essentially an unpolarized signal and a polarized signal. And then there's some early universe models, in particular models which kind of involve some kind of large spontaneous CP violation in the early universe, which would actually predict a polarized signal. That could also kind of give you a handle on discriminating between different signals. I don't know if that answered your question.
Yeah, sure. Thank you.
Any more questions?
Yeah, I have one. Well, first of all, thanks for the talk. It was a very novel theme for me, and more like than a specific question. It's like a question of I'm going to ask for your opinion. I'm a master student, and I'm researching PBH, primordial black holes. And well, I don't know if you have put some effort in that line, but I know that one formation mechanism for PBH is the gravitational collapse of cosmic strings. And well, how do you see that scenario? Do you see it like possible at all, or it's really with a low probability or something? I know that a recent paper say that if PBH forms from the collapse of cosmic strings, they are going to the resulting PBH are going to have higher spin, and that's not really coherent with the observation by LIGO and Lisa. So, well, it's more like an opinion question, but
right. So I think there's several interesting points there, right? So, okay, so I think with the cosmic strings that I'm discussing here, they do not form black holes, right? They simply the loop just the loop shrinks by emitting gravitational waves, and then kind of once the loop kind of shrinks to become extremely small, it can just completely evaporate, right? So here you would not have relic black holes, but I do know that there are other scenarios, right? In particular, I know that there was a recent paper, I think it was maybe Dvali and company, where they kind of looked at like some strong gauge coupling, and you would kind of have these long flux tubes, which could then kind of collapse into collapse and form primordial black holes, right? So just to distinguish it, you do two scenarios. Then regarding the second part of your question, so the spins, yeah, so I think that's actually something which is going to become extremely interesting, right? So I think with the data that is currently published, and when we have some measurements of the spins of the black holes that have been observed, they tend to come with very big error bars, right? But this is going to get a lot better when we have, and the reason they have large error bars is simply that there's degeneracies there. So the more detectors you have in a network, so meaning kind of the more kind of different angles you have on your gravitational wave event, you can break these degeneracies. So in particular now with CAGRA coming, so currently we have the two LIGO detectors in Virgo in Italy, but Virgo unfortunately has a sensitivity which is quite a bit worse than the two LIGO detectors. But now we have CAGRA coming online, or which is already online in Japan, and we'll have LIGO India eventually. And with that, I would expect that the measurements of the spin are going to get a lot better. And also we're just going to, simply because kind of the sensitivity is growing, so our effective detector volume is growing, we're going to have a lot more data and a lot more statistics. And then I think we will be able to make statements about a kind of spin distributions and stuff like that, right? I think it's slightly too early at the moment, and because the error bars are still so big, I mean, it's hard to say something with really a lot of statistical significance. But definitely, I think we will be moving in that direction. I think that's a very interesting question. Yeah, I mean, one complication, I think. Yeah, I mean, one complication with primordial black holes, or one open question is always kind of, okay, how do you produce them in such a way that they kind of have an interesting abundance, right? Because if you produce too many, they just rule out because they overclose the universe. And if you produce too few, then okay, you just have a very, very small probability of ever seeing them. So kind of to get something which is an interesting range is I think a very non-trivial question. That's kind of my thoughts on that. I don't know if that's what you're asking.
Yeah, thanks.
Any more questions? So actually, I have one. Could you go to this slide 15? Here, yes. Under this cosmic magnetic field, how can one be sure that this photon that is generated is actually coming from a gravitational wave source and not another process?
Very good. Yeah, very good. So so at the moment, this is what we're only putting bounds, right? So as long as we put a bound, it's fine, you know. So essentially what we're looking at here, we're looking at the Rayleigh-Jeans tail of the CMB spectrum, and we're looking for essentially a temperature excess, right, at these frequencies. And actually, I mean, both these experiments, so both EDGES and Arcade did see an excess, right? I mean, EDGES even by a factor 2, and Arcade also had a small excess in photons. Now, simply because we are so far away from any reasonable gravitational wave signal, we decided to kind of take the observed excess simply as a statement about the current accuracy of the experiment, right? About essentially the current error bars of the experiment. It's kind of a conservative approach. But yeah, I mean, but yeah, and kind of then of course it was a big discussion. What are these extra photons that they see? And yeah, then I mean, most likely there are some astrophysical mess because astrophysics is kind of complicated, and you have to subtract foregrounds, in particular in EDGES, right? The foreground subtraction is very, very difficult. So I think that is going to be the biggest challenge in improving these bounds, right? It's not so much building a better experiment or bigger experiment or whatever, right? It's understanding the foregrounds and kind of asking, can we actually fundamentally get better? Can we understand the foregrounds to this level? Kind of the reason why we focused on the Rayleigh-Jeans tail of the spectrum, or the Rayleigh-Jeans tail of the CMB spectrum, is that at least conceptually, kind of you can measure something there, which you know is not like conceptually you can get down to values below the BBN bound, but it relies on really understanding your foregrounds very well, and that's a very, very non-trivial issue. So I'm not sure actually how much further one can push these bounds, right? Or if maybe this is already close to the limit of this technology.
Okay, thank you. Okay, I think we're good on time. So thank you again, Valerie, and to everyone for coming today. Have an excellent day, depending on where you are, and hope to see you again in the next seminar. Bye.
Thank you, goodbye.